Okay, Bismillahirrahmanirrahim. Um, Let us begin from, sorry. Okay, Bismillahirrahmanirrahim. Um, any questions? Are there any questions before we start? Remember, the homework is due tomorrow at 5 p.m. Homework 1. Um, what else? Any other question? There will be no tutorial tomorrow. Sorry, today, because we did one yesterday, which covered the homework. So there is no need for one today. Okay. Any other administrative issue? Okay. All right. So last time we were discussing this at the end of the lecture, we got a bit sort of confused. So let me just clarify this. So we were talking about parameterization of points on a plane. Okay. And we said if there are a bunch of 3D points, but those 3D points do not fully span the 3D space, they span a 2D subspace, which means they lie on a plane. That's the linear algebra way to say that they lie on a plane, which means they span a subspace which is two-dimensional. Okay, it doesn't have to be axis aligned. It can be at a tilt, but it's a two-dimensional subspace, right? So that's the subspace pi, which is parameterized by the plane. Now we want to parameterize these points in 2 dimensions because essentially they form a P2 space, which is embedded within this P3 space. Okay, so how do we do that parameterization? So I said the points x, which are all these orange points, they lie on a plane pi, and so they can be written as, my claim is they can be written as x is equal to mx. That is not a surprise because in general, this mapping where I want to write these 3D points as 2D points. So if I take an arbitrary 2D point and multiply that, so the 2D point is a 3 vector, so I should multiply it with a 4x3 matrix to get into a 3D point. So there must exist some matrix, if there is this mapping, there must exist some matrix M of dimension 4x3, which will translate between these 2D points to 3D points, right? So that aspect is clear. So that's why I'm writing it as x is equal to mx. Now I'm saying that M is really the 4x3 null space of the vector pi transpose. That is pi transpose M is equal to 0. What is the argument for this? So the argument for this is that any point that lies on the plane should have the equation pi transpose x is equal to 0, right? If x lies on the plane, then pi transpose x should be 0. Now, if I want to parameterize these points, the orange points on the plane, what I really need is 3 points on the plane, because 3 points on the plane will define that plane itself. And I can make 2 vectors out of those 3 points if I want to. If those points are a, b, c, the middle one is a, then b minus a is that vector and c minus a is this vector. Okay, so those 3 points will uniquely define the plane, and everything on the plane can then be written as the linear combination of those 3 points. Okay, they essentially form the basis of the plane, and that's what I'm after. And so for each of these 3 points, if those 3 points are x1, x2, x3, then pi transpose x1 should be 0, pi transpose x2 should be 0, pi transpose x3 should be 0, because those points are on the plane. I write all of them as columns, so then I'm saying pi transpose m, the whole thing should be 0, because those 3 columns are on the plane. Okay. Now if I'm able to write any 3 points like that, then every other of the orange points can be written as a linear combination of them. Okay, so that's why I'm saying pi transpose m, where m is those x1, x2, x3, pi transpose m should be 0. Now if pi transpose m is 0 and pi is just one row, then m is the 3-dimensional null space of pi transpose. Is that argument clear? Okay, so that's why this holds. This is no different than you can write a line as a parameterized form. You can say alpha a plus 1 minus alpha b is a parameterized form of a line. Okay, which helps you linearly interpolate between the 2 endpoints of the line. So essentially, I'm linearly interpolating between, if I choose M as 3 vectors, then I'm linearly interpolating between those points to reach any other point on the plane. Okay. All right. So how will I find M? By the way, M is not unique, right? I can take any 3 non-collinear points on the plane, and that forms my space, basis space. So so M is, it's not that for one particular plane I'll have one particular M. I can actually have a lot of different forms of M, all of which will allow me to move on this plane in a parametric form. What that essentially means is that there is really no condition that I should put the axis here. I can put it anywhere. There is also really no condition that the axis should be orthogonal. It could be anything which is not the same vector itself. Okay, so I just need 3 independent vectors to be able to span this space. All right. 3 independent points which will form, by their subtraction, it will really form 2 vectors to span the space. Okay, so is that clear? So the question is, how will I find M? Well, I reached this equation by saying I want to span this plane, but now from this equation it's clear that M is the 3-dimensional null space of pi transpose. So I'll just find the null space of pi transpose, which means if you give me pi transpose, I can do its SVD. I'll find 3 values which are non-zero, which are 0, 3 singular values which are 0. I'll find 3 vectors corresponding to that in the V transpose matrix, 3 rows of V transpose which will be corresponding to those zeros. I'll pick those. That's the way to get the null space. How to get the null space? In general, if you want to find the null space, MATLAB has a function null of that matrix. But one of the ways to do it, there are several ways. One of the ways to do it is, I mean, you can find it, let's say, by solving this homogeneous system, right? But one of the ways to do it also is take SVD, singular value decomposition. Now, the middle matrix in SVD, the S matrix, when we have U, S, V transpose, so the S matrix has singular values along the diagonal. Singular values are really square of the eigenvalues of the original matrix times its transpose. Okay, so when I get singular values along the diagonal, if there is a null space, then there will be as many zeros along the diagonal as the dimensionality of the null space. So let's say the matrix is 5 by 5, but only 3 rows were independent. So what will happen is that you will get a 5 by 5 S, but 3 values on the diagonal will be non-zero because there were 3 independent dimensions there, and the other 2 rows were written as a linear combination of those. So you'll get actually 2 zero values. And the vectors in V transpose, the row vectors in V transpose that correspond to those values, yani, let's say those values are at position 4 and 5. So the 4th row and the 5th row of V transpose will be the null vectors, okay, or the right null vectors. And if you want the left null vectors, then the columns corresponding in U to those 0 values will be the left null vectors. Okay. So it is clear. We generated a bit of confusion here yesterday, so I wanted to clarify this. This is, by the way, a very practical and useful way. So if I ask you in a homework, which I will in the next homework, inshallah. So if I ask you in a homework, generate points on a plane, generate random points on a plane, and then we want to image them. Okay. So there are several ways to do that. One of the ways is I want you to generate random points on a randomly oriented plane. Okay, so one of the ways to do that is, well, okay, let me generate points on the xy plane randomly, which means I choose x and y values randomly and make z value 0, and then rotate this whole 3D structure to some arbitrary orientation, and those will be points on the plane. Okay, but another way to do it is this: generate random small x vectors, okay, because those are 2D random points, and then multiply it with a matrix M, and that will be corresponding to some plane. So those points will get rotated onto some plane. Okay. Of course, I can also ab initio generate them. I can say the plane equation is pi 1x plus pi 2y plus pi 3z plus pi 4 is equal to 0. So let me choose any x and y arbitrarily and then solve for z, because the plane has 2 degrees of freedom. So points on the plane have 2 degrees of freedom. So let me choose 2 of them independently, x and y independently. Then solve for z. Z would be pi minus pi 4 plus minus pi 1 x minus pi 2 y divided by pi 3, right? So that would be the solution of z. So I'll choose x and y independently and solve for z. Okay, but it's much more convenient to just generate random small x vectors and multiply them by matrix n, and they will all lie on a plane. If you want them to lie on a particular plane, take the parameters of that plane pi and find its 3-dimensional null space to get m, and then multiply by that m. So it's a very practical trick, and it comes in handy. All right. Any questions? All right. So let's move forward. We started talking about 3D transformations. That's the topic we want to wrap up, and so that we can we understand 2D and 3D vector spaces, and then we will talk about cameras, which really relate a 3D space to a 2D space. Okay, that's what a camera by definition is. Okay, so 3D transformations, I said, is well, some of them are a straightforward extension of 2D. There is really nothing new here that I have to say, except there is an additional coordinate, right? So scaling is Sx, Sy, Sz, and there's an additional Sz column here. So it's a 4x4 matrix in homogeneous form in P3, and translation is Tx, Ty, and Tz in the last column. Again, I have a 4x4 matrix, so I can write translation as a multiplicative form, the same as what we did in P2, right? When we start talking about rotations, I'm not particularly talking about 3D skews, even though I could, but there isn't a direct application that I'll be talking about those, so I've just ignored it. I mean, think of skews as part of the general affine transformation in P3. The general affine transformation in P3 will have how many parameters? 8, 9, 15, 9. We can decide this by democracy, right? Vote on it. Yeah, 9 really, because 3 rows. Sorry, 9, not 9, 12 really, because there will be 3 rows which are fully filled. The last one will not be, because the last one is what will generate the projective distortion. So, like I had a 2x3 matrix for the general affine transform in P2, I'll have a 3x4 matrix for the general affine transform in P3. The first 3x3 block is a multiplicative transform where you can do rotations, scalings, shearing, and so on. And this column is the translation. Okay, so it's 3x3 for the multiplicative part, 3x1 for the additive part. So it's 12 parameters. Okay, that's kind of why democracy doesn't work. I didn't hear a 12 in the suggestions. There was 8, 9, 15, all over. Okay, this is not a political science course, so we'll just take that comment back. Okay, so when we start talking about rotations, there's something new here in 3 space compared to 2 space, because 2 space has very restrictive rotations. It's only in one plane that you can rotate. So the form of the rotation matrix was very simple, and it was quite simple to understand. It's a bit more complicated now, even though by analogy you can see that it's similar. Okay, so let's first, to derive rotations, I'm sure you have done this somewhere in some course before, but I want to highlight a few points which will be very useful in our treatment later. Okay. So what I'll do is, to derive a rotation matrix, I'll first talk about, because now rotation is about an axis, it's not about a point, it's about an axis, right? So let me consider first, for simplicity, just the rotation about z-axis. Okay, so when I talk about rotation about z-axis, here I have a right-handed coordinate system. What do I mean by right-handed coordinate system? If I put my wrist on the origin, curl my fingers from x to y, through the smaller angle between them, because I don't want to go this way, 270 degrees, I'm going 90 degrees through them. So curl the fingers of my right hand from x to y, then z goes in the direction of the thumb. If that happens, then x, y, z is a right-handed system. If I switch the axis, I say my system is really y, x, z, then that would be a left-handed system, because I can't curl from y to x and go in the direction of z the way I've drawn it. Okay, so that would be a left-handed system. In this course, we will just make all our treatments in right-handed systems, just to avoid any confusion, even though that's not always the case. Airline industry, avionics, when they talk about the roll pitch yaw of the aircraft, their convention is they always use left-handed system to describe the rotations. It's their choice. You could have left-handed or right-handed system. We'll just use right-handed systems. That's the more common form in most textbooks on computer vision. Okay. All right. So I'm saying I will rotate about z, which means this point x, y, z will map to x prime, y prime, z prime, okay, by an angle theta. What's the sense of positive rotation here? So so one thing I observe about this rotation is that the z coordinate will not change. Okay, the positive rotation is that I'm sitting on the axis, looking towards the origin, then counterclockwise is positive. Okay, so if I sit on the positive side of any axis, an axis is passing through the origin, so there is a positive side and a negative side to it. Okay, so I sit on positive z, I look towards the origin, then counterclockwise will be considered positive rotation. That's the convention we are following. That's why you see the diagram that positive theta is going from this way to that way, counterclockwise. Okay, because the clock direction. So we always say clockwise, right? But it's only clockwise because we always look at it from the front. If the clock was transparent and I was looking at it from the back, then it would be, the clock would be running anti-clockwise, right? So there is a directionality to your viewpoint when you talk about clockwise and anti-clockwise. All right. So in this case, what will happen, because I'm rotating about z, then z coordinate will not change. Okay, which means z prime would be equal to z before and after rotation. And then if I ignore that, because I already know what the z coordinate is, then the x and the y prime coordinates are exactly behaving like they would in a 2D transform. Okay, because they are on a plane and they are behaving in 2D way, regardless of whether they were actually on the xy plane or somewhere in front of the xy plane, but they are behaving in a 2D way in a plane parallel to the xy plane, because the z coordinate is not changing, so they will not go out of that parallel plane, right? So therefore I know how to compute them. My x prime should be equal to cosine theta x minus sine theta y, 0 z, and then y prime should be sine theta x plus cosine theta y, exactly like I do in 2D with 0 z, and then z prime is equal to z, so that's why I put a 1 here, so that z prime becomes equal to z, and then the last row is just to maintain the 4x4 homogeneity size. Is this clear? So it's straightforward extension. If you rotate about z-axis, it's a straightforward extension of how you did this rotation in P2. Now, of course, so that's the sense of the positive rotation. So the positive rotation is counterclockwise when looking down from the positive side of the axis of rotation towards the origin. We'll always use this convention again in a right-handed system. If I switch from right-handed systems to left-handed systems, actually this minus sign switches position. Because you are getting an additional reflection, which is a -1 being multiplied. So you get a bit of slightly different matrix. So I don't recommend, let's just stick to one convention so things are clear in our head. Okay, so so that was rotation about z-axis. These are the equations you get, and this is the matrix form of rotation about z-axis, counterclockwise, looking from the positive side of the axis towards the origin. How about I rotate about x-axis or rotate about y-axis? How do I get those? Okay, so if I want to do those, well, the simple way to derive them is that I'll just do a substitution of coordinates. Okay, so in this figure, what I'm saying is that what was originally z is now y, what was originally x is now z, and what was originally y is now x. Okay, notice that I still have a right-handed system. I've been careful to do this substitution. Okay, because if I curl the fingers of my right hand, placing it at the origin from x to y, I get towards z. So had I flipped x, y's and z's here in this substitution, I would have gotten a left-handed system, and then I wouldn't be able to directly write an analogous here. So I don't want to do that. So I did this substitution a bit carefully. Okay. In fact, this is kind of like a rotation of how I wrote x, y, z. So so my x, y, z was a right-handed system. So the substitution I did is I took z to this side. I said the new system is z, x, y. Yani x becomes z, y becomes x, and so on. Okay. If I do these types of rotations on my coordinates in text, the right-handedness of the system is maintained. If I were to flip two of them, then it will become a left-handed system. Okay. All right. So now that I've done that substitution in the figure, I'll do exactly the same substitution in this equation, and I'll derive the rotation about y-axis. Okay. So I just did that. I replaced x prime by z prime, x by z, y by x, and so on. Okay, so what I get is y prime is equal to y instead of z prime is equal to z, and I get this equation. And now all I have to do is write it in the matrix form, and I did that. Okay. Notice this matrix is slightly different. No, it's not really. I mean, y prime maps to y, but you were used to seeing the top right one as being negative. Here, the top right one is not negative. This one is negative, but that's okay. This is the equivalent that you would get. Okay, for rotation about y-axis, counterclockwise, so on, in a right-handed system. Okay, and then I want to derive the rotation about the third principal axis. So how do I do that? X, y, z. I now substituted instead of z, x, instead of x, y, and instead of y, z. I did another one of these. I took y to this side, so I got a y, z, x system. Again, verify that right-handedness is maintained the way I did this substitution. So I can just directly do this substitution. Instead of x prime here, write y prime. Instead of x, write y. Instead of y, write z, and so on. Exactly did that substitution. I get this equation, and that comes out to be this system. X prime, because I'm now rotating about x, the x coordinate is an identity element in the matrix. The x row and column is an identity element, and y and z rotate according to a 2D rotation in the yz plane. Is that clear? No issues? Yeah. No. This is how it turns out. I did it in front of you. This is how it turns out. I can't do anything about it. I can't wish it was here. Actually, the reason for that is that you are in a this was an odd column. The one was in an odd column, and you are actually now in an even column, right? So remember how you do determinants. There's a plus sign, minus sign, plus sign, minus sign. So it's kind of analogous to that. Okay. All right. So now I know I've extended my rotation. There was rotation about a point in 2D, so there is rotation about an axis on 3D. So if the rotation, if the axis of rotation is one of your principal axes, either x, y, or z, I know how to set up the rotation matrix for that. Okay, and of course I can concatenate these rotations like I can concatenate any matrix. Okay, so for example, if I was asked to rotate about x by gamma, followed by a rotation about y by beta, followed by a rotation about z by theta. Okay, so I will do the first one here. So I'm saying rotation, I'm using the convention rotation about this axis by this angle, just to write it in short compact form. Okay, so this is the rotation about x is done first. Oh really, I said gamma, so this is having gamma, sorry, that's a mistake. Okay, so the rotation about x by gamma, rotation about y by beta, rotation about z by theta. Okay, I'm writing these in this order. This is the first transform, the second, and the third one, because that's how transforms multiply. And my claim is rotations from a group, so this will still be a rotation. Okay, it will still be some complicated one rotation, which is not about the principal axis, it's about some other axis. In fact, I can do this multiplication and it will come out to be something like this. It's still the multiplicative part is a 3 by 3 term. I just multiplied them out to just show you that in this order, this is what it will come out to be. Okay. really the terms here are non-linear because there are cosines and sines involved. But if you were writing numbers, these numbers would just multiply and give you another matrix. Those three matrices, because they were rotation matrices, each one of them will be an orthonormal matrix with determinant +1. Okay. When you multiply orthonormal matrices, you still get an orthonormal matrix, and you multiply things of determinant +1 with each other. The determinant of the product is the product of the determinant, so you still get a +1. Yeah.
So when you can do rotation matrices, always do the rotation matrices?
Yes, yes. Rotations form a group. So by multiplying pure rotations together, you will never get a transform which is not a rotation. It's very easy to think about that in 2D, right? I rotate by 10 degrees, then I rotate more by 20 degrees. Well, that really is equal to rotation by 30 degrees. The same applies here in 3D.
So, but rotating about a specific form, like I rotate about 20 degrees, then about this one.
Well, when you rotate about something other than the origin, that's not a pure rotation. The matrix is no longer orthogonal. Okay, because there is a translation component involved, and that translation could be very large. Okay, so some of the properties of rotation matrix that we want to look at. Well, rotation matrices are orthonormal with a determinant of +1. That holds for 2D case. That also holds for any matrix in 3D. That also holds for rotations in higher dimensions. Okay, rotations in higher dimensions are dealt with by analogy, really, because we can't like visualize them what they mean. Okay, so because rotation matrices are orthonormal, so it follows that the inverse of a rotation matrix is its transpose. You should try to prove this. Maybe it's actually quite straightforward that an orthonormal matrix inverse will necessarily be its transpose, because every row is size 1. So when you multiply with transpose, the 1, 1 row is really the L2 norm of the first row because it's being multiplied with itself. Okay, so that since its norm is 1, so you'll get a 1 on the diagonal terms, and you'll get 0 otherwise, because those are dot product of two different vectors in the same matrix. So really what that means is that because the rotation matrix is always orthonormal, which means it's orthogonal, its rows and columns are orthogonal mutually to each other, as well as they have a norm of 1. Which means that the rotation matrix, I mean this rotation part, which is a 3 by 3 part, the rotation matrix has 9 terms, but it has only 3 freedoms, because there are 6 orthonormality constraints. By that I mean, by freedoms we mean, degrees of freedom, we mean that how many terms can I pick independently. So even though there are 9 terms, I can't pick all of them independently. Right? Why? Because the sense of that is, as soon as I pick these two, well, the third one has to be such that this column has a norm of 1. As soon as I pick these 3, well, this column has to be such that the dot product of this and this is 0. Okay, so there is a restriction of freedom. You can't like arbitrarily pick all 9 terms. That would not necessarily be a rotation. Okay, so the 6 orthonormality constraints are that all the dot product of each column is 1. That was I mean by I is equal to k. Okay, so that means that the element, let's say 1, 1, 1, so 1, 1 with 1, 1, 1, 2 with 1, 2, 1, 3 with 1, 3. That sort of dot product will be 1. And if j is if I is not equal to k, which means you are doing the dot product of 2 different rows or 2 different columns, that would be 0. Okay, so that's the 3 constraints that you have. You can do it either column wise or row wise, but that's 3 constraints saying each column has a norm of 1, and 3 constraints saying the dot product of column 1 and 2, the dot product of column 1 and 3, and the dot product of column 2 and 3 should be 0. So that's a total of 6 constraints. So on 9 terms you have 6 constraints, so you are left with 3 freedoms. Okay, and that makes sense. In P2, how many freedoms did we have in a rotation matrix? We had only 1 freedom, which was the angle here. Here, since there are 3 principal axes, there can be an angle on each one of them. So that's the 3 freedoms that you have in a rotation matrix. Okay? All right, more properties of rotation matrices. I've already said this. Concatenation of rotation matrices is also a rotation matrix. That is a matrix multiplying 2 rotation matrices together. maintains orthonormality and it maintains the determinant of +1. Okay, so this is easy to prove. All you have to do is multiply two general orthonormality matrices together and say that orthonormality is maintained in the product also. And the determinant of A times B is the determinant of A times determinant of B. So if both the constituent matrices had determinant of +1, then +1 times +1 will remain +1. Okay, so you're not gonna. So that tells you that multiplication of rotations together will remain a rotation, and that's one of the key properties that lets us know that rotations are a group, along with other properties that the inverse exists and the identity exists. What's the identity rotation? What's the identity of rotation? A rotation by 360 degrees, which is really rotation by 0 degrees, right? Which is what? Which is an identity matrix. It's the matrix identity. 1, 0, 0, 0, 1, 0, 0, 0, 1. That's an identity rotation. Okay? So identity exists, inverse exists, associativity exists, and closure exists. So rotations form a group. In fact, there are special names for these groups, right? SO3 and so on. There are those types of groups. Okay. One thing that I want you to, one thing which is very useful in our course, I want you to kind of see this clearly. Okay. Build this picture in your mind of how you interpret a rotation matrix. Okay. So this is a rotation matrix. What is it? What is it like? What is it doing? Of course, this is not rotation about one of the principal axes, because if it was rotation about one of the principal axes, then the row and the column corresponding to that principal axis should have been 0, 0, 1 type of, it should have been a row or column of an identity matrix, and I don't see that here. Okay, so I realized that this is a rotation about something else. But how do I know it's a rotation? Well, I can test. I can take this matrix, multiply it with this transpose, and I'll get identity. Okay, I can take this matrix and pre-multiply by its transpose. I should still get identity, and I can find the determinant of this, and I'll get a +1. So if I do those tests, I will convince myself that this is indeed a rotation. Okay, now it is a rotation, but how do I see it? What do I do to understand what's the nature of this rotation? Okay, yes, there's a question. No, because the determinant could, so you could have an orthonormal matrix with determinant of -1. Yes, so it's in the orthonormality. If you test for orthonormality, an orthonormal matrix by times of transfer can have a determinant of only either +1 or -1. And -1 means in addition to a rotation, there is a reflection involved also. That's the sort of matrix you need if you want to convert between a right-handed system and a left-handed system. You have to have a reflection somewhere. Okay. All right. So one very useful picture that I find very handy to work with is the following. Okay, it's built from this observation. What does, if I apply a rotation matrix to a vector which is really the first row of the rotation matrix itself? Okay, what is R11, R12, R13? This is really the first row here. So which means I'm applying this rotation matrix to a point which is really it's a vector which is really the first row of that matrix. Okay, because that's how you apply a transform. You multiply it by a vector. Okay, pre-multiply by a vector. So I can apply it to any point. All points in the space will move when I apply this. So I'm applying it to that particular point, which is actually defined by the first row of the matrix. You understand that? Right? So what will I get? I'll get, because rotation matrix is an orthonormal matrix, what I get in the first row is R11 square plus R12 square plus R13 square, which is really 1, right? Because the norm of every row and column is 1. And then in the second row, I'll get really the dot product of the first row and the second row. as the second element, which is really 0 because it's an orthonormal matrix, and then in the third I'll also get 0. So I really get a 1 0 0. Okay. What is 1 0 0 in a 3 space? It's the x-axis. It's a point along the x-axis. It's a vector in the direction of x-axis, right? So which means, what has this rotation matrix done? It has affected some rotation, but the effect of that rotation is that the point defined by its own first row rotated, when I applied this rotation, it rotated onto the x-axis, right? So I get some sense of what this rotation matrix is doing. This rotation matrix is going to move that point, that particular point, which was the first row point. It's going to move that point onto the x-axis. It's going to collapse it onto the x-axis. Not collapse, rotate. Collapse is different. Okay. Similarly, if I take the second row and apply the rotation matrix on it, apply that transform on the point defined by the second row, that's going to move on to the y-axis, just by property of orthonormality only. It's going to move on to the y-axis. And if I take the third row and apply the rotation matrix on it, it's going to move on to the z-axis. Okay. So from that I get this result. A rotation matrix transforms its own rows onto the principal axis. It transforms the first row onto the x-axis, the second row onto the y-axis, and the third row onto the z-axis. Okay. The sort of picture that gives you is this: if I'm given a rotation matrix, I can visualize the vector made by the first row, I can visualize the vector made by the second row, and I can visualize the vector made by the third row. Necessarily, these three vectors will be orthogonal to each other, because that's the nature of a orthonormal matrix. Okay, so they form 90 degrees with each other, but they are in some orientation in the space. And what this rotation matrix, the effect of this rotation matrix is that it transforms the space such that these three move onto the principal axis. Okay. All right. So that's one way to think about this rotation. Any questions? Is that clear? Okay. Now let's talk about. I talked about rotation about x-axis, rotation about y-axis, rotation about z-axis. But what if I have a problem where I want to rotate about some arbitrary axis, which is none of the principal axes? Okay, so how do I do that? Well, any combinations of rotations is also a rotation. We have already seen that because there is closure, and that closure follows from the fact that orthonormal matrices will multiply to make another orthonormal matrix. Okay, so therefore, I'm writing that in English, right? The orthonormality closure property. Any combination of rotations is also a rotation. Hence, it can be described, because it was really three rotations, okay, by about the principal axis, or maybe even more, okay. But the net effect is still a rotation, so it must be rotation about some axis. A rotation should have a fixed axis by definition, okay. So therefore it can be described as a rotation about a single axis, and let me call that n, n1, n2, n3, by some angle theta. Again, the sense of positive would be that I would sit on the positive side of that axis, look towards the origin, and define rotation in the counterclockwise direction. So the question is, how do I find this n? Now n has three parameters: n1, n2, n3, and theta is the fourth parameter. So it looks like I have to describe rotation by 4 parameters, but that's not the case. The degrees of freedom do not change by a mere change in representation. Okay, so and you can see that without loss of generality, n could be a unit vector. It's still an axis of rotation, which means n has two parameters only, because one parameter can be reduced by the fact that the whole vector is a unit vector. You can pick two independent terms and choose the third one such that it remains a unit vector. And so n really has 2 degrees of freedom if you want it to just define an axis. It just has 2 degrees of freedom, and the third parameter is theta. So the degrees of freedom, even in this form of setting up a rotation matrix about n by theta, remain 3, which is, if that was not the case, that would have been a cause of concern for us, right? So it's not. Okay, so how do I rotate about an axis n by theta? Now, the problem is, I know it's a rotation, but somebody gives me an n, a vector n and a angle theta. I want to come up with that rotation matrix. How do I do that? Understand the problem? Okay, I'm given n and theta. I want to come up with this 3 by 3 matrix, which is the rotation, that the effect of that rotation is that it will rotate about n by theta. Okay, so the way to do that is, well, number one, set up rotations such that n rotates onto one of the principal axes. This problem is kind of analogous to, in 2D, how do I rotate about a point, which is not origin. So I know how to rotate about origin. Then I say, okay, you give me another point and you want me to rotate about that. I'll first move that point to origin, then do what I know how to do, rotate about origin, and then undo that transform. Okay, so I'm going to do the same thing here. I want to rotate about an arbitrary axis. I will say, first move that axis onto one of the principal axes, because I only know how to rotate about principal axis, I don't know anything else. So I'll rotate this axis onto one of the principal axes, then do what I know how to do, right? Rotate about that axis by one of those Euler matrices that I showed you, and then undo whatever transformation I did in step one. You are very right. It's a good point. It might require a translation. If the axis was passing through the origin, then by a pure rotation I can rotate onto the principal axis. But if the axis is not passing through the origin, I would have to translate that axis to pass through the origin, then rotate it, because I know only how to rotate about the origin, and then I do it. Okay. All right. So I would set up a rotation that n rotates onto one of the principal axes. Let's assume that the axis is passing through a region. So how would I set up that rotation? How? How? Okay, so there are two ways here. I mean, if you look at graphics text, they describe this problem as, okay, you can, so if I wanted to, uh, if I wanted to take these axes, right? These are my, oops, I just dropped the y-axis. So these are my principal axes, okay? And this was the axis about which I want to rotate, right? Okay, so first thing I want to do is I want to bring it, let's say, onto x-axis, okay? So the way to do that ab initio would be that, okay, let me do the projection of this onto this plane. Okay, so let's say this is x, y, z, so I have a rectangle system. So let me project it onto the xy plane. Projection onto xy plane is very simple. I just drop the z coordinate. I make z coordinate 0, then it's projected onto the xy plane. Okay. Once I project onto the xy plane, I take that vector, which is now really xy0 if this tip was xyz, so that vector is xy0. I take the dot product of that vector with the x-axis to find this angle, cosine theta, right? That's it. So I find the angle. Now, once I found the angle, I rotate about z-axis by that angle, so this will come onto this plane. Okay. Once I've done that, so I've done one rotation to bring it onto this plane, then I find this angle, again by a dot product, and I rotate about this axis to bring it onto the x-axis. Okay. That's one way. But what I find is actually an easier way than that. I know that a rotation matrix transforms its own rows onto the principal axis. So if I want to rotate this onto the x-axis, I just write this as the first row of the rotation matrix. Okay, of any rotation matrix. So I set up a rotation matrix where I write this green vector as the first row. Of course, normalized, because in the rotation matrix I can only enter normalized things. Okay, so I get that. So I get the first row. Then what do I need to do? Well, how do I get the other two rows? I actually don't know how to get the other two rows, but the other two rows, the only thing I know is the other two rows actually are not unique. The only thing I know is that they should be orthonormal to this. Okay, So I pick two vectors which are orthogonal and also normal. Yeah, I mean, they have length 1 to this row. How do I pick two vectors which are orthogonal to a vector? Yes, those vectors should have a dot product of 0. So the way to do that really is, the simple way to do that is pick any vector. So let's say this vector is A. Oh no, it's not A, it's N. So I will take N in its normalized form and write that as the first row, right? That's okay. Okay. Now that's just N hat. Okay. Now I want to pick two other vectors which are orthogonal to N hat. Okay. So how do I do that? Well, the first one can be picked by saying pick any other vector A which is not N, which is not just a scale factor of N. So pick any other vector in space. Well, this was that vector. So pick any other vector. Just change one coordinate and that will be a different vector. It will necessarily not be in that direction. So pick any other vector A and just find N cross A. N cross A is something orthogonal to N. Okay? Let's say whatever N cross A comes out to be is B. Then just find N cross B. Or, no, sorry, just find A cross B. Okay? And that will be another vector orthogonal. Okay? Should I do A cross B or N cross B? I have N. So I picked another vector A and I did this. So that cross product is going in this direction. Yeah, so I should do N cross B, not A cross B, right? I should do N cross B and I get the second vector. Okay? Now the only, so you can get two rows like that, you can normalize them and that will set up a rotation matrix. Okay? The only thing that you need to be careful about here is that maybe that rotation matrix end up, it's an orthonormal matrix because you ensured orthonormality by construction. Okay? The only thing you need to ensure is that is the determinant plus 1 or minus 1. So once you do that, you can check the determinant. If the determinant comes out to be minus 1, you can just switch these two rows, the row number 2 and row number 3, and then the determinant should be fixed, and that's a rotation which will rotate N onto the x-axis. It will do on the x-axis because I wrote N as the first row.
So we also need to count as B and the other.
Yes, you would need to do that. So when you take A, you should normalize A, and then you get B, and then you should normalize B also because N and B should have could have two different directions. Let me just do one thinking here. Have I said this correctly? So this is my vector. I take another vector, take this cross product, so that's coming this way. Okay, and then so this way is orthogonal to N, and then yes, I will do N and cross product of N and A, and that will be another orthogonal vector to N. Yeah, so this is okay. Yeah. No, but it's simple cross product, so there is no issue of known and unknown. You know everything about it. Pick any arbitrary A. That's what I'm saying. Pick any arbitrary A, which is not equal to N as a scale factor. So it's a vector in a different direction than N. Take their cross product. Ultimately, I'll drop A because A is not appearing in my matrix. I'll drop A. So I'll get a B and then I'll get a C by N cross B, and B and C will appear as two rows. As long as you can ensure orthogonality, any way to pick orthogonality. Okay. Now, this choice of row number 2 and row number 3, by the way, is not unique, right? Because once I fix an axis, there are lots of orthogonal vectors to this which are orthogonal to this axis, right? They could be any rotation in that plane. So that's why I picked an arbitrary A. If I pick some other A, I'll get two other orthogonal matrices. But that's okay. It doesn't really hurt me, because all I want is to rotate onto the x-axis, regardless of where the y and z axis, which orientation they are. But I'll save this rotation with me, do the rotation about x-axis by theta, and then just take the transpose of that rotation and undo it. Okay. So then I'll rotate about that axis by theta, and I'll undo the transformation in step 1. There is a shortcut to this, which is called the Rodriguez formula. I'm not proving it, even though we could prove this, but I'm just stating this for reference because people talk about the Rodriguez formula, so you should know. Rodriguez formula is the whole solution to this. Yani the way to come up with that rotation matrix about axis n by theta in one step. Okay, and what this really says is I'm writing it as r n theta, where n is a unit vector. Okay, so it's really I, which is a 3 by 3 matrix identity, plus sine of theta. Theta is your angle of rotation. So sine of theta times this skew symmetric matrix formed by n hat. What is this matrix? It's defined here. This is a skew symmetric matrix. Remember in the tutorial I talked about there are some certain special matrices, and one of them is a skew symmetric matrix. A skew symmetric matrix is that matrix where the matrix is equal to its transpose with a negative sign. So the terms along the diagonal are negatives of each other. There's minus nz here, so there's nz. There's ny, so minus ny. There's nx, so there's minus nx, nx. Okay. So this matrix is purely defined by n, and we call it the skew symmetric matrix of n. Okay. So this is also a 3 by 3 term because this is a 3 by 3 matrix formed in this way from n, and this is sine theta plus 1 minus cosine theta into n, the skew symmetric matrix of n multiplied by itself. That's what nx square means. Okay, so that's like a direct way to get rotation matrix about n by theta, and I'm not proving this, but if there is a need, we could do that in the tutorial or otherwise if somebody is interested. Okay, so now you know how to rotate about x-axis, how to rotate about y-axis, how to rotate about z-axis, and how to rotate about any other axis. In fact, you could pick n in this formula, you could pick n as one of the axes and you'll get one of those three matrices that we first talked about. Okay, so the opposite problem of that, because a complicated rotation matrix can be thought of as a rotation about an axis n by theta. So I first described, if I'm given n and theta, how do I set up the matrix? The converse of that, given a matrix like this, how do I find n and theta? So how do I find the axis of rotation from a rotation matrix? How do I find what is the axis of rotation of this? And how do I find the angle of rotation about that axis? Any ideas? How would I approach this? Why? Which property? Not the eigenvalue, the eigenvector. Okay, so yeah, that's very good. So the eigenvector of a matrix A, if x is an eigenvector of A, then Ax is equal to lambda x. Yani x does not change direction. Okay, so the axis of rotation should not move during rotation, which means R of n should be equal to n, which means n is an eigenvector of R with an corresponding to an eigenvalue of 1, because Ax is equal to lambda x as the eigen property. If Ax is equal to lambda x, then x is an eigenvector of A, where lambda is a scalar. So, but because from my observation I know that Rn should be n, because the axis of rotation does not move during rotation. Okay, so that means that rotation matrix, I can find that eigenvector of the rotation matrix, which is corresponding to the eigenvalue of 1, and that will be the axis of rotation. Okay, so hence n is an eigenvector of R corresponding to the eigenvalue of +1. A rotation matrix always has, I did this in the tutorial, for 2 dimensions, I found the eigenvalues of the rotation matrix. They come out to be cosine theta plus iota sine theta and cosine theta minus iota sine theta. So a 3D rotation matrix always has 3 eigenvalues. One of them is +1, and the other 2 are cosine theta plus minus iota sine theta. Okay, you can see that, let's say, by observing the rotation matrix about x-axis. Okay, So the rotation matrix about x-axis is only 2 by 2 rotation matrix in 2D. So that part should have the same eigenvalues. And the third is identity, which is 1. So the third eigenvalue is +1. Okay, and just by every other rotation matrix is a rotation of that matrix, and just by orthonormal multiplication, the eigenvalues would not change. Okay, so in summary, I mean, let's that's a complicated argument. In summary, a rotation matrix will always have one eigenvalue which is real, and that's +1, and it will have two other eigenvalues which are not real. They are complex, which will be cosine theta plus iota sine theta and cosine theta minus iota sine theta. Okay, this kind of makes sense, because suppose you thought, how come there are two complex values? Why didn't I have three real eigenvalues? If there were three real eigenvalues, that would mean that there are three axes of rotations of that matrix, which means there are three vectors in space which do not change when rotation happens. And we know that that's not the case. When rotation happens, there is only one axis that does not change. Everything else changes direction around that. Okay. So a rotation matrix has the following three eigenvalues. They are +1, cosine theta plus iota sine theta, and cosine theta minus iota sine theta. This is quite straightforward to show for, let's say, a rotation about z-axis by theta. In fact, I did part of that in the tutorial, and I showed the cosine theta plus iota sine theta case. So the angle of rotation of the axis. So I know how to find the axis end. I'll just do an eigen decomposition and find the eigenvector corresponding to the eigenvalue of +1. How do I find the angle of rotation? Well, I can do that by the remaining two eigenvalues. Okay, because theta appears in the remaining two eigenvalues. Okay, so I'll show everything about we did about rotation matrix by some examples. So it's concrete. Okay, so this is my rotation matrix. I picked that up. I get that in MATLAB. I typed it in MATLAB. I got that rotation matrix. Okay. So first, I'm writing now MATLAB code. Okay. So first, I will verify whether this is a valid rotation matrix or not. Okay. So how do I do that? I just do R times R transpose. R transpose means the prime symbol means transpose. So when I did R times R transpose in this matrix, I got this. Which, if you realize, I mean, notice that you did not get perfectly zero values here. MATLAB gave me something 10 to the minus 17, but 10 to the minus 17 is like 0.00, I mean 16 zeros and something, which is kind of numerically practically zero. At least I'm okay that it's zero. The physics people might not be, oh, but I'm okay that it's zero. Okay. All right. So this is what I practically got, because it's a numerical computation. Okay. Even though I had been careful in generating, I did not type these numbers up to only this precision. Actually, I cheated. I first generated an orthonormal matrix from MATLAB. So this matrix was orthonormal up to a precision of like 16 decimal values or 17 decimal values. Okay, because that was the precision of the number being used in MATLAB at that time. And so therefore I got this. Had I typed these numbers only up to these 5 decimal places, these values should have been a lot larger. They would still be 0.00 something, but they would be like 10 to the minus 5 order type of thing. Okay? And I can do it the other way around, R transpose R rather than R transpose, and that should also be identity, and again I get something pretty close to identity. Okay? So that tells me that yes, it is at least an orthonormal matrix, and then I can do determinant of R and I get +1. So that means, okay, there is no reflection involved, it's a pure rotation. Okay, I'm just giving this example so things are a bit concrete in your mind rather than just arbitrary. Okay, so now I have that. Let me try to find its axis of rotation, because I don't know where the axis of rotation is. So how do I do that? I say V comma D is equal to eigen of R. EIG is a function. So when I do eigen of some matrix, I get a matrix of vectors, which is a matrix of V vectors. In the matrix V, I get a matrix of vectors which are eigenvectors, and I find in D I get along the diagonal I get eigenvalues. So notice what I got this vector, which is a complex. It has complex elements. I got this vector which has complex elements. This is the first vector. This is the second vector, and I got this which is purely real elements. Okay. And if you look at the eigenvalues, this is a complex eigenvalue. This is a complex eigenvalue. Iota is involved, but this is a real eigenvalue. So the eigenvector corresponding to the real eigenvalue is the axis of rotation. That's my n. So my n is really minus 0.04, minus 0.48, and 0.87. That's my n. I just read it from the eigenvectors. Yeah? Can I do what? I just did eigenvectors of R. So this is a function in MATLAB. It returns you the eigenvectors in V and the eigenvalues in V. Okay? So the eigenvectors are, the first eigenvector is complex, the second eigenvector also has complex element, the third eigenvector is purely real, and I can see that the first eigenvalue is complex, the second eigenvalue is also complex, the third eigenvalue is a real number of +1. Okay? Is that good? Okay, so what I would do is let me verify whether this is a valid axis of rotation or not. How do I do that? I took my original R and I multiplied by n. What I should get is n, and yes, indeed this is the same one. Okay, so if that wasn't the case, I would have been like upset. But this verifies, right, that it's not. It's good. All right. And I can also check that. One other way to check it, instead of visually checking it, I can just take that n, the original n, and r times n, and subtract them and find the norm of that. Because they should be equal, the norm should be 0, and indeed I get 0. 10 to the minus 16 is kind of 0. Okay, so I did L2 norm. This function is, norm function takes a vector and which norm you want to find. So I found L2 norm, which is like x squared plus y squared plus z squared. I mean, it's that sort of norm. Square root, the distance formula that you said. Okay, so I found the axis of rotation. That's good, and I verified that it is the correct axis of rotation because it does not get impacted by that rotation matrix. It does not move under that rotation. Now I have a slightly difficult problem now of what's the angle of rotation. Okay, so how do I find the angle of rotation? I can do that by looking at the other two eigenvalues. The other two eigenvalues were minus 0.5 plus minus 0.8 iota. These are the other two eigenvalues, and I know that these are cosine theta plus minus iota sine theta. Okay, so which means that I can, so notice that the cosine value is negative. This real number is the cosine theta part. Okay, so I notice that the cosine value is negative, which means that the angle is either in the second quadrant or the third quadrant. That's where the cosine is negative. Okay, it starts from the positive quadrant, and then for two quadrants it's negative, and then it comes back to positive. So that means my angle is going to be in the second and the third quadrant. And what I could do is I could do that. I take that value, which is d1 comma 1, which is this thing, this whole thing. I take the real part of that, which is just this thing. I take the arc cosine of that, cosine inverse of that. That comes in radians. I wanted to do in degrees, so I did radian to degree conversion, and I got 124. Okay, but there are two solutions here because it could either be in the second quadrant or in the third quadrant. So in the second quadrant, I got the solution of 124. So in the third quadrant, it would be 235. Both are, because when I fix an angle, the curve cuts it at 2 points. Okay, so I'll always get two solutions. Now, which one is right? I don't quite know. Either could be. It's right that if I knew which one was, if the eigenvalue did not have this plus minus thing, I could say the sine theta term will tell me. Okay, but if I go to the next quadrant, the sine theta term becomes minus sine theta, and so I don't know whether this was the plus eigenvalue and this was the minus eigenvalue. They just flip, and so I can't even tell by the sine theta term. Okay, because they're symmetric in their sign, so they can just switch order, and then I can't ambiguate between them. So to check, I can just check for consistency with Rodriguez formula. Okay, I can take my n, which is the third column of V, really, and then I find theta from that. This is in radians, and then I compute my skew symmetric matrix from that n, which is this. Okay, it's already in the normalized form because the MATLAB function of I gives you a vector in normalized form. So I didn't have to like divide by the norm, but I could have. So I make this skew symmetric matrix. and then I find that R by, this is the Rodriguez formula, okay? I3 means identity 3 by 3 plus sine theta times nx plus 1 minus cosine theta times nx. And I notice I kept theta in radians because cosine and sine function expect value in radians. And so I get this, which is actually not the same as the original matrix. Okay, so that means that this theta that I computed, which is 124, is not the correct theta. So I'll choose the other one. This was the original matrix. This is what I got. Notice that the signs are flipped and so on. There is some problem with this. So the second quadrant solution did not pan out. It did not quite work. Okay, so then I can try the third quadrant solution, which is 2 times pi minus theta. I just move it to the third quadrant and then do the same thing, and then I get exactly the same R. In fact, I got exactly the same R. I tried doing norm of the original R minus this R, 2, and I get 0. Okay. So is that clear? That's all about rotation. So hence the axis of rotation is this, and the angle of rotation is 235.46 degrees.
Do we always have to check this Rodriguez formula?
I would recommend that's the check. There might be some other ways, but this is an easy, straightforward check. You can write it as an algorithm.
But then we can we do directly from the Rodriguez formula? Can we solve it all directly?
No, I'm given R, so I'll have to do like an inverse of the Rodriguez formula, and that's a quadratic equation in n, so that will be more complicated. This process that I did is quite straightforward. I just found that in that. Yeah. No, there were some negative signs which were in odd places. Right? Notice that minus, are they? Oh yeah, it turns out it's maybe it's not perfect. I wouldn't expect such perfectness by chance. Yeah, maybe it is the transpose. I'm not sure. We'll have to prove it. Okay, so summary. We are done with our discussion of 3D rotation matrices. In fact, 3D transforms because that's all I wanted to say about 3D matrices. So this is like your वो पंजाबी में कहते हैं बूटी जो इम्तिहान में लेके जाते हैं. I don't know if you're familiar with that term. Right? You should not be maybe. But this is like the summary slide of everything. When you are preparing for the exam, you can just look at this, right, and just understand. So rotation about principal axis are written as these matrices, and they are about origin in right-handed coordinate system counterclockwise when looking towards the origin from the positive axis. That's the sense of what this matrix means, okay, in terms of positive rotation. Rotation is an orthonormal matrix with determinant of +1, and it has 3 degrees of freedom. You understand that. The inverse of rotation matrix is its transpose, because that's true for any orthonormal matrix. Concatenations of rotations is also a rotation. In fact, rotations form a group. A rotation matrix transforms its own rows onto the principal axis. I gave you that interpretation of how to think about a rotation matrix. Any 3D rotation matrix can be described as a rotation about an axis n by an angle theta. Okay. To rotate about an axis n by an angle theta, you can rotate the axis onto the principal axis, either by composing an appropriate matrix through cross products, or you can do that sort of projection thing that I gave you an idea of. Then rotate about the principal axis and then undo the earlier transform, or you can use the Rodriguez formula. Okay. To compute n and theta from the 3D rotation matrix, n is an eigenvector corresponding to the real eigenvalue of 1, so that's easy to find. Theta can be computed by the other two eigenvalues, which are cosine theta plus iota sine theta, and to disambiguate the angle values, which quadrant you are in the solution, you can check for consistency with Rodriguez formula. Okay. All right. Last thing here. like we talked about hierarchy of transforms in 2D, we can also talk about hierarchy of transforms in 3D. So this is like an equivalent table of what I showed you in 2D. The first group is translation, which is I pipe T, but this is now 3 by 4 rather than 2 by 3. In the previous case, this has 3 degrees of freedom. Why? Because the translation vector now has 3 values and orientations are preserved like before. Then you have rigid body transform. We also call that Euclidean transform, which is R pipe T, which is a 3 by 4 matrix that has now 6 degrees of freedom. Why? Because 3 coming from translation and 3 coming from rotation. Okay, and lengths are preserved here. Then you talk about similarity. Similarity is still one scale factor because similarity means you have equal scaling on all axes. Okay, so one additional scale factor, which means 7 degrees of freedom, and angles are preserved here. Then the general affine transform in P3 space is a 3 by 4 matrix that has 12 degrees of freedom and it preserves parallelism. So parallelity of planes will now be preserved under an affine transform. It will be like I have a cube and I squish it like this, skew it like this, but the planes remain parallel. So parallelity of planes is preserved. And then the general transform in P3 is projective, which is a 4 by 4 matrix. Instead of 16, it has 15 degrees of freedom because it's a projective equation, it's a homogeneous equation. And the fundamental property of a projective transform is that straight lines will remain straight lines. Straightness of a line is preserved under projectivity. I actually wrote it in code, so that's like the complete explanation of it, right? If I'm given an n and a theta, so two variables are defined, n and theta, then Rodriguez formula is exactly this, right? I3, which is identity 3 by 3, plus sine of theta times nx, plus 1 minus cosine of theta times nx times nx. And what is nx? Nx is this matrix, 0 minus n3, the third element of 3, n2, semicolon, so I'm in the next row, n3, 0 minus n1, minus n2, n1. Right? So actually, you can talk about all equations and so on, but if you can't code it, that means you didn't understand it, right? So that's one way to check. Any higher level concept that I'm talking about here, in your mind, you should do two checks. One, when I write a matrix equation, first thing you should do is, are the sizes okay? If the sizes don't add up, that means you don't understand something about that equation, right? That's a very basic 0 level check. And the second thing you have to think about is, whatever I'm talking about, can I code this or not? Do I have a good enough understanding that I can go out from here and write code for this? If you can, that's a good position to be in. If you can't, you just feel that you understand this math, actually you don't, right? Which is actually very easy in math. I mean, I could just throw like equations at you and talk loudly and convince you, you have to understand that. And then you will feel like, oh yeah, I understood it. Right? But if you are unable to code it, there is a problem. Okay? Because this is not really a math class. All right. Okay, done. I want to... okay, so the next thing that we'll talk about is we have been waiting for it, right? Oops. The next thing that we'll talk about is camera models. So we know how 2D spaces work and how to do transformations in 2D. We know how 3D spaces work and how to do transformations in 3D. And a camera is really a transformation from 3D to 2D. Well, you thought camera is something you can go and buy. No, it's a matrix. Okay, all right, we'll stop here. Any questions? All right.